So we've talked about how the sun actually lives its life right now in the main sequence. Uh, but you should also know that the sun doesn't stay the same way the entire time because it is using up the hydrogen in the core. Now, if you remember, there's like a thermostat inside there that what happens is that you're fusing hydrogen at just the right rate to maintain stability in there. And eventually, though, things kind of get in the way and the process starts to break down a little bit. So, what we're going to talk about now is how the stars age, how they age a little bit, and then how they age off the main sequence, what happens to the future of the sun. And so, we know that primarily what makes a star instead of a protostar or a failed star is that hydrogen fuses to make helium. And so that is the main process, but there's only so much hydrogen there. Eventually, it's going to run out. What happens to a star, as it turns out, is dominated by the initial mass of the star, what we call the initial mass function. So low mass stars tend to form slowly. They have less gravity that pulls themselves together. We talked about how that works. High mass stars actually form faster. Again, we mentioned that before the spring break. Mid-mass stars, they kind of like the sun, they're in between. But the other thing that happens is the low-mass stars, because they have so little gravity, they don't have to fuse hydrogen very quickly to support themselves. So even though they don't have much mass, they fuse hydrogen very slowly and they live much longer than the high mass stars. The high mass stars have to fuse a lot faster, and so even though they start off with more mass than the low mass stars, they run out of it quicker because they fuse so furiously fast just to support themselves against gravity. So the lifetime of a star is highly dependent on the initial mass. So consider our own sun and what happens to it. Right now, then the sun is fusing hydrogen into helium, what we call the proton-proton chain. And we talked about this in our previous chapter. Originally, the sun had 75% of its mass all the way through the sun as hydrogen, and 25% of its mass is helium. Today, the innermost part of the sun, right near the core, is like 30-something% hydrogen by mass. And the outer parts do not participate in nuclear fusion at all, and so they stay the same proportion of hydrogen and helium, but the inner part has become more and more helium rich as time passes. Likewise, it originally was 25% helium all the way through, but at the core, it's gotten up to like 60-something% helium by mass. Now, by number of atoms, it still is mostly hydrogen, but eventually it's going to be mostly helium inside. So what happens to it? Well, inside the core, we have hydrogens, and it was mostly all hydrogens, only a little bit of helium. Now we're getting more and more helium. What happens is those heliums start to get in the way of the hydrogen atoms. So when they start to get in the way of the hydrogen atoms have a tougher time getting together to fuse. That means that fusion actually slows down compared to what it normally would be going with that temperature and pressure. When that happens, there's not enough fusion to support against gravity, and so gravity squeezes the core, and the entire core squeezes a little bit smaller, and that makes it hotter. So the core gets smaller and hotter, and what happens is that makes the fusion speed up, and now the sun maintains stability again. But the core is hotter, and that means that there's excess of heat inside the core of the sun. That heat has to get out somehow, and so the sun eventually gets a little bit brighter and slightly larger. So today, the sun is nearly 40% brighter than it was when it formed. It's about a little over 5% hotter than it was when it formed. So the sun is gradually getting brighter and is getting hotter. Well, what effect does that have on Earth? Well, it has a lot to do with Earth. Because what happens is the sun drives the climate of the Earth. So if the sun's getting brighter and hotter, that's going to result in warming of the Earth. Well, that actually turns out to be a very important thing, because what happens is that Earth would have been much cooler in the past than it is today. Well, if it were that much cooler, then it should have been frozen over. Well, because there was quite a lot cooler and dimmer earlier. Well, the Earth wasn't frozen over. And that's because the atmosphere of the Earth used to have more carbon dioxide than it does today. So over time, the atmosphere of the Earth has been lessening the amount of CO2. Remember, CO2 is a very powerful greenhouse gas. So when the sun was less bright, the Earth actually retained the heat better. And so that maintained a balance. One of the big issues with greenhouse gases and global warming is a lot of people don't realize what you want is the proper balance so that we have just the right balance of greenhouse gases. It's not that none of it is what we want. We want just a tiny little bit to maintain the right temperature of the Earth. If the Earth had no greenhouse gases, then that would mean that we'd actually be too cold. Too much greenhouse gases, we're too warm. Now, this is actually good because throughout, the recorded history, in fact, for millions of years, as the sun's been getting brighter, the greenhouse gases have been dropping, and that's been maintaining a proper temperature of the Earth. Now, I should also mention, just as a side note, the proton-proton chain that we talked about in the previous chapter on the sun was the proton-proton 1 branch, or PP1 branch. And that's when the hydrogens come together to make a deuterium. The deuterium forms together to make a hydrogen, which makes a helium-3. The helium-3s come together to make a helium-4, a couple leftover hydrogens. So this is your normal proton-proton chain. There's a couple of other proton-proton chains that happen. Because the sun has more helium-4 in it as time progresses, it occasionally happens that one of those helium-3s, instead of hitting another helium-3, hits a helium-4 with enough energy, it fuses into a beryllium. Beryllium then grabs an electron, becomes a lithium. Lithium rapidly fuses with a hydrogen and splits into two heliums. In fact, the idea that lithium can fuse with hydrogen was the basis behind the very first hydrogen bomb that was built. And so this chain starts to dominate when the core of the sun gets hotter than about 14 million Kelvin. And so right now the sun's not quite that hot, and so the proton-proton 1 chain dominates. This will start to. Another thing that's going to start dominating when the core of the sun gets even hotter is that this beryllium, rather than grabbing an electron, could actually grab a hydrogen and become a boron. The boron then becomes, it radioactively decays by giving off a positron, neutrino, becomes a beryllium, which then splits into two hydrogens. And again, this is beryllium-7, which is stable. Beryllium-8 is not stable. It fissions almost right away into two heliums. And so that's the proton-proton chain, 3. Now, you don't really have to know the details of these different proton-proton chains. Just know that there are alternate ways you can get nuclear fusion inside the sun, and these other fusion processes will dominate at different temperatures in the future. Right now, 86% of the sun does the proton-proton chain that we talked about in our previous discussion about the sun and nuclear fusion in the sun. And only 14% does proton-proton 2, and only a tiny fraction of percent proton-proton 3. Eventually, though, another cycle starts to kick in, and that's what we call the CNO cycle. Carbon is not very common in the sun, but there's a little bit of carbon. And so what will happen is a carbon will grab a proton, basically a hydrogen nucleus, become nitrogen-13. And then the nitrogen-13 is going to, nitrogen-13 will grab another proton and become a carbon-13. And then the carbon-13 will radioactively split and give off a positron, okay, and a neutrino becomes nitrogen 14, which then grabs another proton, becomes oxygen 15. Oxygen 15 then grabs another proton, okay, and what happens is that could remain an oxygen 16, but it typically doesn't. What happens is if it hits fast enough, it splits, becomes carbon 12 and a helium. And so what will happen is the cycle then produces the cycle will produce a sequence here of start with carbon, and then over time it grabs 4 protons, so 4 hydrogens, and then when it's done, it's split. It's given off a couple of neutrinos, and it's created an extra helium. Now, once in a while, if it goes slowly, you do get a little bit of oxygen. So the process does sometimes give you a little bit of oxygen in there, but primarily this is a process of fusing hydrogen at super high temperatures. Now, what's going to happen is eventually the sun will completely run out of hydrogen in the core, and so after about 5 billion years, that's where the sun is right now. And so you have more helium than hydrogen by mass. Now, by number of atoms, they're still about similar. Eventually, though, after about 10 to 12 billion years, the interior of the sun will be almost all helium. Well, in that case, the hydrogen fusion will stop. Long before then, though, Earth is dead. Because in 5 to 7 billion years, we will run out of hydrogen and the sun will start to burn out, but only in about 1.5 billion years, the sun's going to be already 15% brighter than it currently is. In that case, the Earth will be so warm that almost all life on Earth that we currently know will be extinguished. In about 3.5 billion years, even the oceans are going to boil away. And then pretty much all life, even the more resilient life, will no longer live on Earth. So even though the sun has between 5 and 7 billion years left, life on Earth probably has only 1 to 2 billion years left before the sun gets so warm that Earth becomes uninhabitable. So the future of the Earth is kind of like West Texas, hot and dry.